Hello everyone, my name is Han and I'll be speaking about exponential integrability of probabilistic integrators for approximate Bayesian inference. This is joint work with Andrew Stewart, Tim Sullivan, and Aretha Teckentrup. The setting of this work is parameter inference for dynamical systems. Suppose we're given a solution Z to an initial value problem or an IVP given by a parameter-dependent vector field f of u. So f as for a given parameter of value u, f of u is a vector field from Rd to Rd, and the goal is to infer the value of this unknown parameter u from j noisy observations, yt1 to ytj, which we use to form a stacked vector of observations in Rdj. And these are observations of the trajectory z at times ti for I equals 1 to j that don't have to be equidistant. So a problem with this is that typically when we want to solve an initial value problem, we need to perform numerical integration of some kind of equations of motion, and we need to use a grid. In the example of numerical weather prediction, we need to put a grid on a spatial domain, and we want to evolve these equations of motion forward in time in order to infer some values of certain parameters of interest that we can then use to make predictions about the future. However, unknown subgrid dynamics, in other words, the dynamics that happen at scales finer than the grid scale, can have some effect on the dynamics that we can observe at the grid scale. And these unknown dynamics that we can't resolve, they will contribute errors to the numerical solution. In particular, if we use this numerical solution for inference, these errors will propagate to errors in inference. This brings us to the traditional approach of using random variables as proxies for unknowns. This is an approach that is implicit in the coin tossing idea, where we model a coin toss as a Bernoulli random variable. Suppose we're given a deterministic integrator psi, which is a function of the time step capital T, the duration of the initial value problem of interest, divided by a resolution of the grid capital N. And basically, using this deterministic integrator, we find the state at discrete time k plus 1 of the discrete approximation Zn by simply applying the deterministic integrator psi to the state of the system, the discrete system, at discrete time k. And we do this in steps of time t over n. Now consider a probabilistic integrator, again based on a given deterministic integrator psi. This gives us a sequence of random variables z hat n. Again, discrete time k plus 1, the state at discrete time k plus 1 is obtained by simply applying psi to the state at discrete time k, but now we add a random variable, psi k, evaluated at t over n, where each psi k is actually a random variable taking values in this Banach space. An example is due to the work of Conrad et al. In their seminal work in 2017, they considered psi k, where the psi k's are actually IID normals with mean 0 and variance decreasing as t over n to the power 2p plus 1, where p now is the parameter of choice that you can set. Larger values of p mean that the variance decreases faster as n increases. The original motivation for this was to use some Gaussian process priors for the uncertainty that we have about the subgrid scale dynamics. An additional benefit of this is that there is a very extensive theory for Gaussian processes. They have very good analytical properties, of which I will mention just one. The theorem due to Fernique, which states that for a centered Gaussian random variable x taking values in a Banach space, there exists sufficiently small lambda such that the squared norm of the Gaussian random variable is exponentially integrable. Let's move on to consider true and random approximate forward models. Consider the true solution operator, or otherwise known as the parameter to solution map S. S maps the parameter space U to the space of continuous trajectories on 0 to t, taking values in Rd. So it sends a single parameter, U, to a trajectory, which is the solution of the initial value problem with the parameter value U in the vector field and in the initial condition as well. We can then consider a random approximate solution operator, Sn omega, which again is a map from the same place, from the same space to the same space, but now it sends a parameter u to a sequence of random variables z hat n, which are defined by the probabilistic integrator that we saw before. We can also consider an observation operator O for the given set of observation times t1 to tj, And that just sends a discrete, so basically it takes a trajectory in this space and it just maps it to the vector of stacked observations. We can then form the forward models G as just the composition of O with S, and the random approximate forward model Gn as the composition of O with the random approximate solution operator Sn. By definition, you can show that the RDJ Euclidean norm of the forward model, the approximate forward model with respect to the true forward model, is bounded above by the number of observations times the sup norm of the error of these two operators, the two solution operators. Now this brings us to the question, under what conditions and in what sense does this quantity here go to zero? Results from the work with Andrew and Tim are as follows. Let's introduce some assumptions on the randomization variables psi k's. The first is a uniform moment bound. This states that for a certain p greater than 1, for a natural number r and c psi greater than 1, we have the following bound on the rth power of the supremum norm of each psi k. And this is valid for any r between 1 and capital R. In particular, the rth moments decrease as something times the time step to the power p plus a half to the power r. Note that psi k doesn't need to be centered Gaussian or IID. However, if we choose r equals to 1 to be equal to 1, then you'll see that the absolute mean must decrease to 0. Even if it's not 0, it must decrease to 0 as n goes to infinity. The second assumption is a continuity at 0 assumption. Basically, it just states that for any k, each psi k evaluated at 0 is 0 almost surely. Now, this brings us to the theorem in the paper with Andrew and Tim. If these two assumptions hold, and if the solution map S is globally Lipschitz, and the deterministic integrator that we use, psi, has order q plus 1, then the rth power of the L infinity norm of these operators is bounded above by some constant times the time step to the largest moment index, capital R, times the smaller of q and p minus a half. A corollary of this is that if we fix an n, a natural number little n, if A2 holds, if the continuity at 0 assumption holds, and if the uniform moment bounds holds for all capital R which are in the natural numbers, then we in fact have a sort of exponential integrability property of this error, and this is valid over all rho in R. Let's review Bayesian solutions of inverse problems just briefly. In an inverse problem, we're given a forward model G, a mapping from the parameter space to the observation space, and we're also given noisy data of the form y equals g of u plus eta, and the task is to solve for an unknown parameter u. To do this, we choose a prior probability measure mu naught on the parameter space u, and we choose a data misfit or a negative log likelihood function phi, and we are given a datum y in the observation space. The Bayesian solution of the inverse problem is the posterior probability measure mu, which depends implicitly on y, but we will omit the y dependency in notation. This posterior is absolutely continuous with respect to the prior, and it has a Radon-Nikodym derivative of this form. And implicitly, the posterior mu depends on the forward model G by the misfit. You can't see it at the moment, but if we consider the example where the noise eta in this equation is mean 0, and so it's a Gaussian random variable with mean 0 and covariance c, then the misfit phi of u is just nothing than the half of the squared quadratic norm c weighted. Let's now think about random posteriors. Suppose we fix a distribution of the noise eta in the observations yt1 to ytj. Then the true forward model G and the random approximate forward model Gn that we introduced earlier produce corresponding data misfits and posteriors. Again, using the example of Gaussian noise, the true misfit phi is just what we've seen before, and the random approximate misfit phi n is what we obtain by taking this formula and replacing the true forward model with the random approximate forward model Gn. This is the formula for the true posterior in terms of its Radon-Nikodym derivative, and we can do the same thing and to define a random approximate posterior mu n on u, just by replacing the misfit phi with the random approximate misfit phi n. So in what follows, let's let nu n denote the distribution of Gn, and thus also of phi n. We want to measure the approximation error of these posteriors with respect to the Hellinger metric. Let M1 of U denote the set of Borel probability measures on U. The Hellinger metric is then a metric on this set, and it's defined in this form. The precise formula isn't very important, it's just to show you what this Hellinger metric is if you're not familiar with it already. The question is now, do we have local Lipschitz continuity, something like the Hellinger metric or the Hellinger distance between the true posterior mu and the random approximate posterior mu n? Can we bound that from above by a constant times the error in the forward models? And the significance of this is that it's important for well-posedness. In fact, it's stronger than well-posedness of Bayesian inference. This is, if you're interested, you can consult Andrew's Acta Numerica paper from 2010. But you can also see papers, very recently published papers by Jonas Latz and Björn Sprunk, who have considered well-posedness in different contexts. Now I can present some results from the paper with Tim and Aretha. So recall that the notation nu n denotes the distribution of phi n. Let's place some assumptions on these misfits. The first is a uniform lower bound. There exists a real number, C0, such that the true misfit phi is bounded from below by minus C0, and nu n almost surely, the random misfit phi n, is bounded from below by minus C0 as well. The next assumption is kind of like a very coarse L1 error bound. For sufficiently large n, greater than n star, there exists an n star and a C1 such that for sufficiently large n, we can bound the L1 error of phi n with respect to phi in a product topology by C1. And the last assumption is an exponential integrability assumption. There exists a rho star in 2, so strictly larger than 2, but finite, such that rho star times phi n is exponentially integrable with respect, again, to the product measure of the prior with this distribution nu n of the randomness. A5, this exponential integrability assumption, is the most difficult assumption to verify. We can use these assumptions to develop an error bound for the random approximate posterior mu n. And the theorem goes as follows. Suppose assumptions A3, A4, and A5 hold. Then we have a bound, a mean square bound on the Hellinger distance between the true posterior mu and the random approximate posterior mu n in terms of constants that we won't go into further detail about, times a sort of product, a weighted, an appropriate bound on the difference between phi and phi n in an appropriate product measure topology between the prior mu naught and the distribution nu n. In particular, we can use this bound to develop a bound on the mean square of the error of the Hellinger distance in terms of a similar bound, but now between the forward models, the true forward model G and the random approximate forward model Gn. And we can do this because you can show that a certain bound holds. You can have control over this error in terms of the error in the forward models. What does this mean? This means that we get mean square error in the random approximate posterior mu n in terms of the error in the random approximate forward model Gn. In particular, this also gives us Lipschitz continuity for an appropriate product measure topology, and this implies well-posedness. I would like to also mention that the conclusions of this theorem hold under weaker assumptions. Let's just go over them very quickly. So the parameters that we need to introduce first are two pairs of Hölder conjugates, exponents, qi prime, and there are two of them. And we also have two scalars, d1 and d2, that depend on these Hölder conjugate exponents, and they're strictly positive. The first assumption is an exponential decay with respect to the prior mu naught of just the negative tails of both the true misfit phi and the random approximate misfit phi n, and it's of this form. The second assumption is a decay condition with respect to the product of the prior with the distribution nu n of the randomness, and it's a decay condition on both tails, on both the negative and the positive tails of the random approximate misfit phi n. And it's of this form. And it's rather hard, visually, it's rather hard to see how one could begin to evaluate this in a reasonably efficient way. So these two assumptions are important because the first yields an important inequality in the analysis that we used to prove the preceding theorem, And the second condition, the decay condition, ensures that the Rado-Nikodym derivative that pretty much defines the random approximate posterior mu n, it's well defined. And therefore it ensures that the random approximate posterior mu n is itself well defined. Now let's just very quickly revisit the stronger assumptions that we introduced before. A3 is a uniform lower bound, A4 is a very coarse L1 error bound, and A5 is exponential integrability on the random misfit phi n. It's the most difficult assumption to verify. We now have a theorem on Bayesian inference with probabilistic integrators. Assume there exists p greater than 1, c xi greater than 1, such that for any r in a natural number, we have the following uniform moment-bound condition. And in addition, we also assume the continuity at 0 condition for all of the randomizations xi k. Then, these assumptions that we saw before hold, and in particular for the random forward model Gn formed in this way, with the random approximate solution operator Sn that we saw before, that's constructed by the probabilistic integrator Z hat n, the random posterior mu n, I'm sorry, there's an error here in this, it should be a measure, so strictly speaking, evaluating at 0 doesn't quite make sense, but I hope you understand what I mean. The random posterior mu n satisfies a Hellinger bound on the mean square Hellinger distance between mu n and the true posterior mu. And the bound is in terms of a constant d times the error between the true forward model G and the random approximate forward model Gn. Let's sketch the proof of this theorem very quickly. Note that the random approximate misfit phi n is automatically non-negative. We're assuming here Gaussian noise, so the square of a quadratic norm is non-negative, and this implies that the first assumption A3 holds. The continuity condition on the randomization variables xi k's and additional assumptions that we're going to sweep under the carpet for the moment, they imply basically what we saw earlier in the work with Andrew and Tim, that we have uniform control over the solution operators in terms of a constant, which I've omitted here, times the time step to an appropriate power. Therefore, for n sufficiently large, we can make this sufficiently small, because we saw earlier that we can bound this quantity here in terms of this quantity. And in particular, this shows that A4, the assumption A4, which is an L1 error bound, is satisfied. Lastly, we have the uniform moment bound condition on the randomization variables xi k's, and this implies an exponential integrability of this error between the solution operators, as we saw earlier. Under the integrability condition, which I'm going to sweep under the carpet again, on phi, and for suitably large rho star, we can show that this quantity here is bounded above by this quantity. And under these assumptions, this quantity is finite, and therefore the exponential integrability assumption A5 is satisfied. This yields, by the Lipschitz continuity theorem that I showed you earlier, it yields control over the mean squared Hellinger distance for the random posterior, and this yields the conclusion that I showed you earlier. So to close this talk, I'd like to summarize. Recall that our goal was to perform Bayesian inference for unknown parameters using numerical solutions of initial value problems, in the case of numerical weather prediction being an example, where we want to infer some parameters that we can then use to predict what the weather will be 24 hours or 48 hours from now. The challenge of this is that because we're using a grid, there are subgrid scale dynamics that we can't resolve, and therefore they are unknown. However, these unknown dynamics can propagate to grid scale dynamics, and therefore the error that we incur by not knowing the subgrid scale dynamics needs to be accounted for. To account for this, we use probabilistic integrators to basically take into consideration the subgrid scale dynamics that we can't resolve. We then perform randomized Bayesian inference using these probabilistic integrators, and then we quantify the approximation error of the resulting random approximate posterior, mu n, with respect to the true posterior mu, in mean square with respect to the Hellinger distance. And we bounded this quantity above by an error in the forward models G minus Gn. So what? Well, in their paper of 2017, Andrew and Aretha considered the case where the approximate random approximate forward model Gn or the random approximate misfit phi n were given by Gaussian process approximations of G or phi. And in particular, because they're working with Gaussian processes, there are very many nice properties that they could take advantage of, such as exponential integrability. In the paper with Tim and Aretha, we showed that exponential decay of negative tails of both the true misfit phi and the random approximate misfit phi n suffice for Lipschitz continuity of random approximate posteriors. This is also assuming, of course, that you have good decay of both tails of the random misfit phi n. And we know that exponential integrability is a stronger condition than exponential decay of tails. We then used basically the r equals plus infinity uniform moment bound on the randomization variables that we used in the probabilistic integrator to ensure that exponential integrability of this quantity of the error in the solution operators is valid. I'd like to thank Andrew and Tim and Aretha, my co-authors of the papers, the results of which I presented in this talk. And I would like to thank very much the mini symposia organizers for extending the invitation to speak at the SIAM-UQ mini symposium on probabilistic numerics, and for also making the effort for organizing this online mini symposium. Thank you for your attention, and I'd like to close with some references.